Stanford University.
All right, there was an issue that came up the last time, and I didn't understand the question. There was a question that kept coming up, and I didn't understand what it was until the very end of the class. And it was an interesting and a good question, so I want to go over it because it is important. It had to do with a spin in a magnetic field emitting a photon. And I maintained that if it emits a photon, remember the way we set things up, we said let's take the Hamiltonian to be omega over 2, let's say sigma z. That has two eigenvalues, plus omega over 2 and minus omega over 2. So the two eigenvalues, let's call it E1 for energy. The lower of the two eigenvalues is minus omega over 2, and the upper one is, let's see, we could call this E minus, and E plus is plus omega over 2. So there are two energy levels. If we drew an energy level diagram, energy, we would have two eigenvalues. It would be 0 over here, but that would not be one of them. And then we would have 1 over here, omega over 2, and minus omega over 2. All right, now what can happen under such, we have not studied this process yet, but let's talk about it for a moment. Given two states like this, it is possible for an atom or a spin or a system with energy levels like this to emit a photon. Emit a photon and go from the upper one to the lower one, if it's in the upper. If it's in the lower state, obviously it cannot emit a photon. It doesn't have the energy to do it. But if it's in the upper state, it can emit a photon. And that photon will have the energy difference between the upper and lower state, so it will have an energy of frequency or energy omega. Sorry, not frequency. It will be frequency, but more important, it will have energy of omega. There's an h bar missing. I've been setting h bar equal to 0. No. H bar equal 1. I've been setting h bar equal to 1. It's really h bar omega, but I'll continue to set h bar equal to 1 because we're all grown-ups and we're not afraid of setting h bar equal to 1, right? What?
It was 0 last quarter.
It was 0 last quarter, yes. It was 0 last quarter, that's correct. Right. Okay, so we draw a picture with a photon, a transition, and a photon being emitted. Now somebody said, what if the spin was not pointed up or down? What if it were pointed, here's the z-axis, what if it were pointed, well, let's say this way, along the x-axis, and then it emitted a photon? Would it not emit a photon of half the energy, namely omega over 2? And the answer is no, it would not emit a photon of energy omega over 2. Let's discuss first what would happen classically. Classically, if we had a rotor, a spinning rotor in a magnetic field that had an energy which was the typical energy would be proportional to the cosine of the angle between the axis of the spin. Here's the axis of the spin. Here's the magnetic field. The energy of that rotating object would depend on the orientation of the spin relative to the magnetic field. The energy would be minimum down, and it would gradually increase until it were up. All right, that's number one. Number two, classically and quantum mechanically, classically the actual value, quantum mechanically the expectation value of the spin precesses around the b-axis with frequency omega. That also happens classically. It's in the classical mechanics notes in the Poisson bracket section where we studied exactly that question. It wasn't called spin, it was called angular momentum. The spinning top does exactly the same thing. And that spinning top, if it really is a little electromagnet, a little magnetic system rotating, it will radiate. In the process of going around with frequency omega, it will emit radiation. At what frequency? Omega. It will emit radiation at and how much radiation will it emit? Now, it's classical. It's not emitting photons. It's emitting classical radiation. And it will gradually, as it emits radiation, fall over until it gets down, and then no more radiation. How much energy will it emit altogether? And the answer depends on the angle that it started at. If it starts up, it will emit altogether an amount of energy that's proportional, essentially, omega. If it's pointing down, it will emit no energy. If it's pointing horizontally, it will emit, let's say, omega over 2. So there'll be a continuous possible value of emission of radiation at the same frequency. Quantum mechanically, it can only emit a photon with whatever energy that photon has. And the answer is it's a related but different answer. If it emits, it will emit a photon of energy omega. On the other hand, the probability of whether it emits is not 1 necessarily. In fact, let's suppose that the initial state is some alpha up plus beta down. If alpha and beta are equal, that corresponds to being oriented along the x-axis. If alpha is 1 and beta is 0, that's pointing up. If alpha is 0 and beta is 1, that's pointing down. An up electron, or an up spin, will emit a photon of of frequency omega, of energy omega. So if there was just the up state, yes, indeed, it would emit omega. If it was the down state, it emits nothing. If it starts in the superposition of states, then with probability alpha star alpha, it emits, and with probability beta star beta, it doesn't emit. What is the average energy? Given that there's a probability alpha star alpha that it emits with a photon of frequency omega, energy omega, and beta star beta that it emits nothing, what is the average energy? And the average energy is the same as the classical energy. The average energy is the same as the classical energy, but each individual event emits a photon of either emits no photon or emits a photon of energy omega. Okay, so this was who asked the question? Somebody here asked the question. Yeah, is that yeah? Okay, so that's the upshot, and it's a sort of internal consistency of quantum mechanics. Now, of course, to really, yeah.
If the electron will emit a photon when it goes down in energy, presumably it could absorb a photon.
Yes. Yes. That's correct.
How precise would that photon have to be to omega?
That depends on the lifetime of the state, and which in turn depends on how strongly coupled it depends on the magnitude of the dipole moment. The stronger the dipole moment, the magnetic dipole moment, the faster it will emit. The faster it emits, in other words, the shorter the lifetime of the excited state will be. It's the inverse lifetime which sets the scale of exactly what you're asking, the precision with which you have to be at exactly. There's a spread in the energy levels. The spread in the energy levels, or an uncertainty in the energy levels, and the uncertainty in the energy levels is inverse to the lifetime of the state. So, right. So you're absolutely right. There is a spread, and it's governed by the energy time uncertainty principle, but we're not there yet. Okay. Whether we get there or not, I don't know. Okay.
Is this phenomenon of photon emission what's used to create an apparatus to detect spin?
In what apparatus?
To create an apparatus that detects spin of an electron.
You could. That's one way. That's one way to do it. That's one way to do it. I decided not to think about that as an apparatus because I didn't like it. It didn't satisfy the rule that, that if you measure a component of spin, you leave the system with exactly that. And after thinking about it, I decided that did not qualify as a genuine measuring apparatus. Yeah. So we're going to come to measurements and the meaning of measurements in a little while, but it would assume, ooh, it's a half an hour gone already. Okay, if there are no more questions, I want to move on to the subject of entanglement. I had a few words to say about the collapse of a wave function. Let's just talk about for a moment the idea of collapse of the wave function. We talked about how quantum states evolve according to the Schrödinger equation. And that is the way they evolve, but that's the way they evolve between events where somebody or something, a detector or an apparatus, or just some other system, an external system, interacts with the original quantum system. So we have a quantum system, we have other things in the world, including observers and including apparatuses, and just including other things. If we take away all the other things, the system might be left in some state, and the system will then evolve according to the Schrödinger equation. And then we may bring back the other things. The other things might be an apparatus. Where did our apparatus go? Our apparatus is hiding, but it could be our apparatus or something else. But let's say it's an apparatus, and the apparatus measures some specific thing. Then what happens during the course of the interaction with the apparatus is a measurement takes place, and the system is left in an eigenstate corresponding to the particular outcome. So, for example, we might start, let's suppose we want to measure L. And our system, after a while, might be in a state, some summation over I, a bunch of complex numbers, alpha sub I, times eigenvectors of L. Eigenvectors of L with eigenvalue lambda sub I. Okay, what's the probability for the outcome of the experiment? The system got here by evolving using the Schrödinger equation. We started it out, we evolved it with the Schrödinger equation, here's what we got at the end of the day, and now we make a measurement of L. And we get some specific value of lambda. Random, we don't know what it's going to be, but it's going to be something. Let's say it's lambda 7. We measure lambda 7. Thereafter, or right after that, the system is in state lambda 7. The course of the operation of measurement is not governed by the Schrödinger equation for the system. It's governed by the nature of the measuring process. Okay? And it simply tells you that you'll come out with one of the eigenvalues as the measured value, and the state vector will be just one of these. Which one? Random. Random depending on the measurement. Now that's funny because you might think, look, well, first of all, let's give it a terminology. The terminology is the wave function has collapsed around one point. It has collapsed around one single eigenvalue. You can't predict which one, but all of the structure here with all the other ones becomes irrelevant, and only one state pops into existence, so to speak. All right, now what's wrong with this? What's wrong with this? Well, there's absolutely nothing wrong with it. It's a correct description of the measurement process. But what is very unsatisfying about it is, after all, apparatuses are just quantum systems. Why do we have two rules for the way systems evolve? One, the Schrödinger equation, and one, this arbitrary collapse of the wave function. And the answer is that if we want to think quantum mechanically about the whole system of system plus apparatus, that's fine, we can do it, and I hope we'll get to it tonight. And then it's pure Schrödinger equation, but we cannot separate the system into just system an apparatus. We have to think about the whole quantum system as being system plus apparatus. That raises the question immediately, right now, how do you combine systems together? If you have more than one system, it could be an electron spin and the apparatus. We have two systems now. Imagine we had a good quantum theory of the apparatus. The apparatus is a physical system. Quantum theory governs it. How do we describe the combined system where we take two components, one spin, one apparatus, put them together? How do we make it into a single quantum system? And then how, with that single quantum system, do we describe this process of measurement? That is has confused generations of physicists, partly because Bohr was very stubborn about this and didn't really quite have it right. And he was a nice man. He was a very nice man. I'm very glad I never met him. No, he was a nice man, but the thing is, he was also a very stubborn man. And in this particular thing, he was mostly right, but here and there he was wrong, and apparently it was very tough to be around him when he was. People tried to explain to him over and over again, you have to think of the combined system, and you have to think of the combined quantum system if you want to understand the quantum mechanics of measurement, and he said no, he didn't believe that. Anyway, combined system. We have two systems now. Let's just not worry about what they are. They are two systems. We'll get more specific in a moment, but let's give them names. Let's call one of the systems A, and A does not stand, it could stand for apparatus, but it doesn't have to. It's just A, system A, and we'll call the space of states of system A, S sub A. S sub A could stand for system A, but now I have it to mean the space of quantum states of the system A. And we have another system I'm going to call I. It's another system I with its own space of states I. The system A has states which are labeled by a basis of states. You choose a basis of states in the system A, and you label them A. A can go from 1 to whatever the number of states of system A is, whatever the dimensionality of the space of states A is. And system I has states I. Any state of system A, if you didn't have I, would be a superposition of these basis states. Any state of system I would be a superposition of these basis states. Okay? How do we put the systems together and make a single quantum system? Well, I'm going to tell you what the rule is. I'll give you a cookbook rule, but it's pretty compelling, and it is the way real things work. Okay? You build a space of states of the system AI, which means A and I together, both of them. That space of states is called, mathematically, it is what is called the tensor product. I'll tell you what it means in detail, but it's the tensor product of the two space of states, SA, and this is the symbol for tensor product, SI. Now, what does a tensor product mean? Well, it means something very simple. It means you construct a new space, new mathematical space, whose vectors are labeled by a value of A and a value of I. In other words, you pair off the basis vectors in all possible pairings, one from A, one from I, and you construct a basis which is labeled AI. If this, let's suppose the dimensionality of this space is D sub A, and the dimensionality of this space is D sub I, or D sub, I guess it's capital A I want here, D sub capital A and D sub capital I. In other words, the number of orthogonal states of each one of these separately. Then what's the what's the dimensionality of the tensor product? dA times di. You get to pick one from A and one from I, like in the Chinese restaurant. One from A and one from I. Okay? And how many are there altogether? dA times di. That's why it's called a product, because the dimensionality is a product. So this is dA times di in dimensionality. These are the basis states for the tensor product. Okay? They're labeled with two indices. Now, you think of them as an orthonormal basis. Orthonormal in the following sense. If you take two such vectors, AI and let's say BJ, where B is another one of the basis vectors of A, and J is another one of these. What's the inner product between these? Let's take these to be normalized vectors. What is the inner product between them? And the rule for a tensor product is the inner product between this and this. Of course, we have to make a bra vector out of it in order to take its inner product. But if we made a bra vector out of this and took its inner product with this one, the rule is that the inner product is 0 unless A is equal to B and I is equal to J. In other words, unless they match. Okay? If they don't match, these might be observably different. For example, if this B was the same as this A, but I was not the same as J, then one half of the system here there would be observable differences associated with observable differences in the subsystem I. So in order for them to have an overlap, B must equal A and J must equal I, and then they're observably the same vector.
Excuse me. Are these arbitrary vectors, A and...
These are basis vectors. These are...
So they're part of an orthonormal basis?
Yes, you could pick any orthonormal basis for this one and any orthonormal basis for this one.
Number of these things we're talking about here.
Yeah, okay. Yeah. But you could pick any orthonormal basis from this one, any orthonormal basis from this one, and put them together this way, and you'll get the same result. It doesn't matter which basis you pick, but let's pick a basis to be concrete. Let's pick a basis. If A and I are not the same as both B and J, the inner product is 0. I can write an equation for that. BJ AI is equal to delta, chronica delta, AB, chronica delta IJ. If I is not equal to J, or A is not equal to B, this is 0. It's only non-zero if I is equal to J and A is equal to B. So these vectors formally, by construction, which means you're simply assigning values to things now, but in a way that is useful, these vectors form, by definition or by construction, an orthonormal basis for the combined system. And this makes sense.
Excuse me, another question?
Mm-hmm.
As you've defined it, it's dependent upon the basis, but I
It does, but actually, as I defined it, let's put it this way, the words dependent on the basis. The construction in the end doesn't. The construction in the end doesn't, and that's not too hard to show. This is, however, keep in mind that these basis vectors are not all of the vectors in the tensor product. You can then take any linear combination of these basis vectors, and they're also a vector in the tensor product. So the general vector in the tensor product is of the form sum over I and A, alpha, let's call it some IA, a general linear combination with coefficients that depend on what's inside here times the vector times the basis vectors. Now, the answer is, if you were to have chosen another basis, another set of bases, you would have gotten exactly the same vectors, except they would have been written differently. They would have just been written in a different basis of the combined system. Changing basis for the individual systems corresponds to a basis change for the combined system. Okay, so that's That's good. And we now have the idea of a tensor product. And I'm going to give you a concrete example now. The concrete example is the next most complicated quantum system, namely two spins. Well, it's debatable whether it's the next most complicated or the next to next most complicated. And the reason I say that is because two spins have 4 basis vectors. You could imagine a system with only 3 basis vectors, and such systems exist. But since we're trying to learn how to combine systems, let's take two systems and combine them, each of them being a spin. So what do we have? We have an electron nailed down at this position over here, and it has a spin, which we're going to call sigma. And it has 3 components, sigma, x, y, and z. So sigma, x, y, and z. Okay. And we have another one over here. We need a name for it. Now, I toyed for a while with calling this one sigma 1 and this one sigma 2, but there were too many indices. Then I had sigma 1x, sigma 1y, but they're bad. So I decided to give this one another name. And the Greek letter that comes after sigma is tau. I don't know if it's the next letter. It's the one in the English alphabet, ST, yeah. So the next one, I think, in the Greek alphabet is tau. And I simply call this one tau. How many components does tau have? Well, tau is also a spin, so it also has 3 components, x, y, and z. Supposing I choose for the basis vectors for each of these the up and down basis vectors. In other words, the states in which sigma z is up or down, and the states in which tau z are up and down. Then our basis vectors for sigma are up and down. Our basis vectors for tau are exactly the same, up and down. And maybe in order to indicate that these are vectors for the system tau and these are vectors for the system sigma, let's use a slightly different kind of bracket notation here. Let's use a curly bracket. I'm going to give that up very shortly. I just want to point out to you that these are different than these. And down. Okay. So, good. What is the basis vectors for the combined system? If we put the systems together, what are the basis vectors for the combined system? There are 4 of them. 2 times 2 is 4. And what are they? They are states in which both spins are up. That's one of them. One spin, and I'll always take the first entry here to correspond to sigma, and the second entry to correspond to tau. Up, down, down, up, and down, down. That's the 4 basis vectors. Each basis vector carrying 2 labels now, a sigma label and a tau label. That's the idea, and it's a very reasonable idea. Yes?
Suppose these 2 component systems interact. Doesn't that change things?
No, the basis vectors stay the same, but the linear combination of basis vectors that are describing the system will change. Yeah. So any state in the space can be written as an alpha up up times up up plus an alpha up down plus an alpha down up plus an alpha down down. That's the most general thing we can write. Let's call it psi. The answer to your question is if you started out with a particular linear combination, let's say, for example, just alpha up, 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 both spins up, and you let them interact, then in general what will happen is these coefficients will change. In fact, it could even happen that after a time, alpha up, up might go to alpha down, down. In other words, two spins up might interact in such a way as to just wind up down. That would not be a change in what the basis vectors are. It would be a change in what the alphas are. Okay, so all right, now there are several questions we can ask. Incidentally, one of the criteria for doing this correctly is that if we take the combined system, but then we only do experiments on one of the halves of it, the other one doing whatever it's doing, and they're well separated from each other. Let's suppose they're well separated from each other, and we do experiments on only one of them. The answers that we get should be the same answers that we got when we didn't even think of it as a combined system. If we have a theory of sigma, which we've talked about now for 5 weeks, I think, and we know all about it, we know how to do experiments on it, and now we think of it as half a system composed of sigma and tau, but sigma and tau are far from each other, let's say. They're not interacting with each other substantially, and we do exactly the same experiments that we've been talking about up till now. We should get the same answers. So we should put these things together in a way which makes sure that the earlier issues, the earlier description of either subsystem is still correct. Now, I'm not going to bother proving that. I think you'll get the idea, and you'll see how it works. And the way we are putting things together does guarantee that. Okay, now we can go in two directions from here. We can talk about the space of states, or we can talk about the observables, and we're going to do both. We're going to do both, but I'll take a vote. How many people want to talk about the space of states? How many want to talk about the observables? We'll talk about the space of states first. You knew I was going to do that. Come on, you knew I was going to do that. All right. Yeah.
One question. Are we allowed to pick left and right for the second one?
What's that? Oh, yeah, sure. There are. Yeah. Supposing we wanted a state which was left for sigma and up for tau. All right? So this would be a state which would be prepared. We have two apparatuses now. I'm always uncomfortable with the word apparatuses. I always think it should be apparati, but I don't think that's right. We have two apparatuses, one that we apply to sigma, the other that we apply to tau. And we now take our apparatus, one apparatus, the sigma apparatus, we point it in the, let's say, the xy axis, not the xy, along the x-axis, and the other one, and we point along the z-axis, and we wind up discovering that sigma was along the x-axis with +1, and tau was along the z-axis also with +1. So that means that sigma was up, but tau was right. How do we make a state which is... So the answer is this. I'll tell you what you do, but then we'll eventually have a mathematics to this. Sigma is definitely up, but tau is a linear superposition of up with down. Easy. You just take up, up, plus up, down. Square root of 2, 1 over square root of 2. You can think of this another way. You can say, think of it as a product of up for sigma and right for tau. Now, what is right? Right is up plus down, right? Right. Right is up plus down. So this can also be written as up times, and I'm going to put a big square bracket around it, up, squiggly bracket, plus down. But if I want to normalize it, I should put a square root of 2 downstairs. So we just think of it as a product of sigma up and tau along the right direction. But that's the same thing here. we have 1 over square root of 2 up, up, that's this one, and 1 over square root of 2 up, down, that's this one. Okay. I'm not sure if this answered your question or not. I think it probably partly did, yeah, okay, right. And, you know, okay. This kind of state is called a product state. It's a product state in which you know exactly what's going on with sigma, namely it's in the up direction, and you know exactly what's going on with tau, it's in the right direction. There's a product state, and it's simply two separate things which were prepared independently, and here it is. A product state is by definition a product. Let's write the most general product state. The most general, this is not the most general product state. The most general product state can be written as follows. Alpha up, up, plus alpha down, down. That's for sigma. And then for tau, let's call it beta. Let's call the coefficients for tau, let's call them beta. Beta up, up, squiggly, plus beta down, down. What does this mean? This means that sigma was prepared in this particular linear combination here. It might have been by holding your detector in some funny angle. And this one is the response to holding the tau detector at some other angle. Had you had only one of these, not the other, you would just have written this down. Had the other one, you would have written this down. Together, you write down the product. That's the rule. Okay, that's the rule. And of course, you know, ultimately these rules are the rules because they agree with experiment, but it's a pretty plausible rule. This is a product. We could also write it alpha up, beta up, times up, up, plus alpha up, beta down, up, down. Do I need to write the rest of it? Well, I will. Plus alpha down, beta up, down, up, plus alpha down, beta down, down, down. All right, now, of course, this is of the form of a general vector, but there's something special about the coefficients here. The coefficients factorize into, and therefore, this is, in a certain sense, special to some extent. Let's see if we can quantify how special. Yeah?
What kind of vector product is that?
That's a tensor product. This is an element of a tensor product, and it's the tensor product of this vector with that vector. It's a vector drawn in the composite system as a tensor product of a vector describing one system and a vector describing the other system. So, strictly speaking, the tensor product is usually used for the whole space. But then you would say this is a product state within the tensor product space. And I'll just call it a tensor product state, or product state. It's not general, and to see how non-general it is, we can count parameters. Given a general system, a general state vector, how many parameters, how many independent parameters does it take to describe it? And the answer is 4 complex numbers. Alpha up, up, alpha up, down, alpha down, up, alpha down, down. I am not assuming that it has this special form. Just general 4 numbers. 4 complex numbers is 8 real numbers. But that's a little too much, because we should assume that the state is normalized. So that's one constraint. And we also know the overall phase is not important. So when you count parameters, you always subtract 2, one for the normalization and one for the phase. 8 minus 2 is 6. 6 real parameters describing a general state of 2 spins. How many here? Well, the state describing the sigma particle, that has 2 real parameters. 4 real parameters for alpha up and alpha down, but then we subtract 2. Same thing here. This is a normalized state, and its overall phase doesn't matter. This is a normalized state. Its overall phase doesn't matter. Altogether, 4 real parameters. It's the same 4 real parameters that you might have guessed if you just said I have 2 spins. Each spin had 2 parameters necessary to write down its state, 2 real parameters. The real parameters could have been the polarization directions of the spin, the axis along which the spin is oriented, or so there are 4 parameters here, but 6 parameters here. That simply proves that not all states are product states. In fact, most states are not product states. We're going to talk about some non-product states soon enough, but this is the notion of a product state. And in the product state, we can really think of separate states for each of the particles or each of the subsystems. But for a more general state, you can't really divide it into a state for one subsystem and a state for the other subsystem. They're entangled. They're entangled in a more elaborate and more, I don't know what the word is, entangled. They're entangled in a more entangled way. We're going to discuss that entanglement. That's a very important concept, of course. Okay, so that's 2 spins. How many parameters? 6 versus 4. They're entangled, right? We've talked about product states. And that's what we know about the space of states of this system. It takes 6 parameters to describe it, but only 4 parameters if it's a product state. Product states are the ones for which you can separately say there's a state for one system and a state for the other system. End of story. Okay, now let's talk about observables. Now we come to observables. What are the observables for this composite system? Well, they must be the same observables as for the separate systems by themselves. In other words, sigma x, y, and z, and tau x, y, and z. They are the things you could measure with 2 apparatuses of the same kind as we used in our experiments on 1 spin. We now have 2 of them, and so we have sigma x, sigma y, and sigma z, and tau x, tau y, and tau z. Let's see if we can figure out how these operators ought to operate on the states of the combined system. All right, now you can sort of guess. I'll spell it out, but here's the rule. Let's take sigma x, and let's apply it to a state of the sigma system. Obviously, it belongs with the sigma system. If it applies to up, it gives down. If it applies to down, it gives up. You can check that. That's the fact that sigma x is equal to 0, 1, 1, 0. This off-diagonal character means it takes up to down and down to up. Right? This is what sigma x does ordinarily if we only had one subsystem. Here's what it does on the combined system. Sigma x on any vector which begins with up and has anything, let's see, which one was A and which one was I? Second one was I? Tau went with I, or tau went with tau was I, okay. So sigma x, when it acts on up I, all it sees is the up, all it sees is the first thing here, and it's completely passive with respect to the second index. In other words, it doesn't even notice the second index. It leaves it the same. It doesn't change it, but it does whatever it should do on the first entry. Likewise, sigma x on down I equals up I. You just take what it did for the single part, for the single spin space, and you just think of the other index as a kind of spectator that just goes along for the ride. Doesn't do anything. On the other hand, oh, let's do one more. Sigma, one more sigma. Sigma z. on up I. Well, what does sigma z do when it acts on up? Sigma z is 1 minus 1, 0, 0. It just gives back up with value 1. So that's just up I. And what about sigma z on down I? Well, what happens when sigma z hits down? Minus down. So this gives minus down I. How about sigma y? What does sigma y? Well, sigma y does something very much the same as sigma x, except it throws an I, not this I, but the numerical complex number I. Throws it around because, what is it, sigma x, this is sigma z. Sigma x was 1 minus 1, and sigma y was equal to minus I, 0, 0. Sigma y also flips up to down and down to up, but it throws in a gratuitous I here and there. Okay, so that's what sigma does. Now how about tau? Well, tau does exactly the same thing, except that the first entry becomes the spectator, and only the second entry gets acted on. So let's do this one. Tau, let's say x on A up. A could be anything. Now, A can be up or down. Doesn't matter. Tau x on A up is equal to A times down, and tau x on A down is equal to A up. All right, let's do tau z on A up equals A up, and tau z on A down is equal to minus A down. And you can figure out the action of the y components of the spin. Straightforward. With this definition, it's quite clear that if you're talking about an observable associated with sigma, that the tau degrees of freedom are completely passive. Nothing happens to them. The eigenvectors of the components of sigma are simply product states of the eigenvectors of sigma times any vector for tau. In other words, for example, the eigenvector the eigenvectors of, let's take sigma y. Ordinarily, the eigenvectors of sigma y are 1i or 1 minus I. I can't remember which one has eigenvalue plus 1 or minus 1, but one of the others. All right. That means the linear combination up plus I down. That's an eigenvector of sigma y. If you want the eigenvector of sigma y, when we're talking about the composite system, it's exactly the same, except you put an I in here, I guess. An I in here and an I in here. Same I. Same I. So, for example, it could be up, up, plus I down, up, or up, down, plus I down, down. The I is a spectator. It just goes along for the ride. Anything which was an eigenvector for the single system remains an eigenvector for the single system, except you'll have to add in the index for the other particle, for the other subsystem. And that's all there is to it. With these definitions, as I said, it's pretty clear that the separate subsystems behave independently, quite independently, as long as you don't let them interact and feel each other or do something interesting with each other, as long as they are kept separated. Okay. Other questions? Yeah.
Those equations, sigma x acting on u gives down, and sigma x acting on
Yeah.
Shouldn't those, since you have sigma x acting on an up vector, shouldn't that result in a superposition of states?
No. Sigma x.
Expanded up in terms of the eigenstates of sigma x, right?
Well, let's just do it by matrices. Sigma x is 1, 1, 0, 0. Up is 1, 0. Okay? Up is 1, 0. What happens? This times this is 0. This times this is 1. So up has gone to down. Okay? Likewise, if we put a 0 here and a 1 here, this would become a 1, 0. So it just takes 1, 0 and flips it to a 0, 1, and back and forth like that. In general, of course, you would be right, but for this particular case, it just gives you back.
I see how the ones and zeros work out, but I'm trying to map that into the physical situation where you're making the measurement of the x direction of a state that's prepared this way. And sometimes get
Well, this doesn't say, let's see. This doesn't say 1, 0, and 0, 1 are eigenvectors of sigma x. Far from it. It's about as far from an eigenvector as you can get. When you act with sigma x on this one, you get a completely orthogonal state. So this is not the rule that says, this is not the equation that says that 0, 1 or 1, 0 are eigenvectors. An eigenvector is a vector which is kept in the same direction by action of the operator. This is, as far as you can get from that, the operator acts and gives you something orthogonal. And that's, okay? All right, you'll have to work that out.
Up is a linear superposition of left and right.
Indeed it is. Indeed it is. Right. 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 That's correct.
That sort of connects to my question before class, which is, so is there any physical meaning to applying an operator to a non-eigenvector?
Well,
what does that operation equate to?
most of the times, that's just an auxiliary operation in some calculation or other. Well, it doesn't have any particular special physical meaning, but in this particular case, what it tells you is 0, 1, and 1, 0 are about as far from eigenvectors as you can get. And what it tells you is that if you measure sigma x in an eigenstate of sigma z, it's as random as it can be. Okay, it's as random as it can be. All right, we're going along good. Yeah.
So in this product notation that you have, what happens if I have sigma x, tau x operating on A?
Say it again.
In the product first equation that you had, tau x on AU gives you AD. What happens?
This one?
Yes. What happens if I had sigma x and tau x operating on AU?
You mean sigma x times tau x? Okay, we could work that out. Oh. Let's do it. It's a little bit late. It's 5 minutes later in the notes, but let's do it right now since we're at it. Let's take sigma x, tau x, and tell me what vector you would like to apply it to. How about up, up? Let's do up, up. What does tau x do? Let's see, tau, I keep forgetting. No, this one, the one on the left is sigma, right? This one's sigma, and this one's tau, right? Okay. All right, so we start with tau. And we hit this. What does tau x do? It operates on this one and leaves this one alone. So this gives us, do I have it wrong? Yeah. It operates on this one and leaves this one alone. Right. Okay, so it gives sigma x, I have not acted with that yet, times, now tau x flips this one. So it's up, down. Okay, now what does sigma x do? It flips this one. So it just gives down, down. Kind of boring, but that's what it does. Let's do it in the opposite order. Let's take tau x times sigma x on up, up. What does it do? It does exactly the same thing. Sigma x hits one of these and flips them, and then tau x comes and hits the other one and flips it. So when tau x times sigma x acts, it gives exactly the same thing as sigma x times tau x. Commutator of sigma x with tau x equals 0. No difference between the order of operations. Let's try it for sigma x times tau z. Okay, let's do it for sigma x times tau z and see what we get. Oh, I have not proved this because I only exhibited for one particular state. In order to argue that sigma x times tau x equals tau x times sigma x, whoops, you would have to show that they give the same thing when acting on any basis vector. It's enough to show that they give the same thing on basis vectors. All right, but that's pretty easy. Not hard to do. You can do it on any basis vector, and you'll find out that the order of operations doesn't matter. In fact, the same is true if you take sigma x times, let's say, tau z. Let's do it again. Shall I take a different vector? Let's take some other vector. Instead of up, down, let's take down, up, and see what it does. And then we'll do it in the opposite order. All right, what does tau z do when it hits this vector here? It only acts on the second entry, and it's a z component, so it just gives +1 on an up, right? So this just gives sigma x times down, up. Tau z on up gives up. So that just goes right through. Then what does sigma x do when it hits down, up? This gets to be a little bit gobbledygook. At this point, my tongue starts rebelling. What does sigma x do when it hits tau, when it hits this guy? It just flips down to up. So it gives up, up, right? Let's do it in the opposite order. Tau z sigma x on down, up. All right, first sigma x. That flips down to up. So it gives us tau z times up, up. And then tau z just gives 1 when it hits the up here. So it gives the same thing again. And you can sort of see why. If they're acting on separate indices here, it doesn't matter which way you order them. This is very general. It doesn't matter which state you take. It doesn't matter which components you take. Any component of sigma commutes with any component of tau. You can check that just by knowing how they act. All right, so we can say sigma anything. I'm not sure what to call the index here. Sigma, I don't want to call it I. We've already used I for something, but sigma n and sigma and tau m. For any n and m, they commute. The meaning of that is that if you have two separate subsystems which are combined in this way, the observables for one and the observables for the other can be simultaneously measured. In particular, if you take the systems and far apart from each other and you treat them as a single quantum system, you would expect that measuring one of them doesn't interfere with any measurement of the other one. And that's what this says, that measuring a sigma does not preclude measuring a tau, and vice versa, for any components of them. So in that sense, they behave like independent systems. You can make any measurement on sigma and any measurement on tau. Yeah.
So what we've got so far is we've got these observables on each independent part of the, on each piece of the system. And we can think about an observable as one part is happening in this system.
Yeah.
Yeah.
And
It's as happy as it was before you added the other subsystem.
Are there observables?
Yes. Yes, that's a good question. Are there observables which are somehow more intimately connected with having both of them? The answer is yes. For example, sigma times tau. Sigma times tau, sigma x times tau x, or sigma x times tau y, that sort of thing are observables that somehow know more intimately about the combination of both of them. And they know, in particular, about entanglement.
You started with independent. You just said spin sigma and spin
Right.
tau. Now, how are you linking them so that they depend on each other?
We haven't yet. We haven't yet. What we've done up till now is do all the ingredients which tell you that as long as you do separate experiments, separate operations on the two subsystems, that they will behave exactly as they would have had the other system not been there. But now you can ask, what about, are there more, in particular, if the system is, the combined system, if it's in a product state, so that each component has its own state vector, then the quantum mechanics of each one of them is separate from the other. They don't interfere with each other. They don't know about each other in any way. That's what this prescription ensures. No, they're not entangled yet. Not if they're product states. Now, what we found out is that the product states are a 4-parameter set. We found out also that the full space of states has 6 parameters. So there are apparently states which are not product states. Those are the states which have, to varying degrees, a degree of entanglement. I'm going to write down now the most entangled state, and we're going to examine it a little bit and see in what way it's odd. Up, down. There are many highly entangled states, maximally entangled states. I'm writing one particular one. Minus, and I'm putting the minus here just because I happen to know that it's has a particular property, which is not so important at this stage, but let's put the minus there. Minus down, up. 1 over square root of 2, of course. 1 over square root of 2 times the whole thing. Now, this state is interesting. It has the property that if you well, it has a correlation. If you know that tau is down, then sigma must be up. On the other hand, if you know that tau is up, then sigma must be down. Now, what does that mean mathematically? We're going to find out exactly what that means mathematically. This is not a product state. There is no way that this can be written as a product of one state. It's a sum or a difference in this case of 2 product states, but it is not a product state. How can we tell? How can we tell? So let's consider the expectation value in a state of the components of sigma. Let's go back to the one subsystem, to the one system quantum mechanics, one spin. And let's ask, what do we know about that? In particular, I'm interested in expectation values of in any state, take a state, and take the expectation value of all three components this is the average value. I'm not multiplying or anything. I'm just considering them individually. Can they all be 0? Can they all simultaneously be 0 for an ordinary state of, for the ordinary two-parameter family of states of a single system? Should we take a vote, or should I just tell you? The answer is no. They cannot all be 0, and here's the reason. Well, the reason is, given any state, there is always a direction in space, in three-dimensional space, a direction for which sigma in that direction, the component of sigma in that direction, is definite and equal to +1. Given any psi, this is what I told you in the very beginning of the lecture, or maybe even before the lecture, given any state, there is some linear combination of sigmas which is definitely equal to +1. Okay. In that case, if I find that particular combination of sigmas, sigma nx, dot sigma into n, that particular linear combination, its expectation value can't be 0 because it's definitely up along that direction. So the answer is, given any state, there is always some direction, let's call it sigma dot n, that depends on psi. It depends on psi, sigma dot n, for which this is not only not 0, but it's equal to +1. The average of sigma dot n is, of course, if sigma dot n is definite, if it's known and there's no ambiguity about it, then the average is just equal to the value that it's known to be. So there is always some n. All right. For any psi, there exists an n such that this is true. Therefore, it cannot be true that all of these can simultaneously be 0 for a state of a single spin. You can't measure them all simultaneously. But if I give you a state, I tell you the state, then you can tell me what direction of space should you orient your detector so that the answer comes out +1. Okay? For example, I could just give you up. Okay, so what direction, if I gave you up, what direction should you orient your detector to? Along the z-axis. What if I gave you up plus down with square root of 2? What direction should you orient your detector to make sure that you get +1? Along the x-axis, right? Okay. What if I gave you up plus I down? I don't know, some either plus y or minus y. Okay, if I forget which one. Given any combination, there are enough directions that you can find the direction for which sigma in that direction is definitely +1, and therefore it cannot be that all of these expectation values are all 0. Why? Because you know that sigma dot n is equal to +1. And that's, of course, just a linear combination of these. Okay, so as I said, it's impossible if we have just a state of one spin, isolated by itself, it's been prepared somehow. However it's prepared, there exists a direction in which the spin is definite and not equal to 0. Okay. What about this state? What about this state by now? Let's take sigma and ask whether any of the components of sigma have a non-zero expectation value in this state. What I'm going to show, I'll tell you the answer right now. We're going to show that all three components of sigma have 0 expectation value in this state. That means the state cannot possibly be a product state. A product state is one in which each component behaves as if it were just a state of the subsystem by itself. This state is going to behave in a way that no simple product state could possibly behave. We're going to find, and so let's do it, okay, let's put, the square root of 2 here is not important. That's not the important thing. We have up, down, minus down, up. We're going to take the expectation value, so that means we have to make a sandwich. The sandwich will have up, down, minus down, up. And in the middle here, we're going to put a sigma. We could do the same with tau. We get the same answer. So let's put sigma z first. Let's put sigma z here and see what we get. First, we act with sigma z. And what does sigma z give when it hits up, down? It just gives up, down, right? All right. All right, so this just gives up, down. But what does it give when it hits this guy over here? Minus down, up, but there's already a minus down, up, so there's a plus. There's already a minus. The minus gets killed. That's over here. And that's the inner product. Let's put some bracket around it. That's the inner product with up, down, minus down, up. Okay, let's calculate it. What's down, up with up, down? 0. What's down, up with down, up? 1. So we get a 1. What's down, up with up, down? Ooh, I got something wrong here. What did I do here? This should be up, down, right? Yeah, up, down. Okay, so let's go back. Up, down with up, down is 1. Up, down with down, up is 0. All right, what about down, up with up, down? 0. What about down, up with down, down? 1, but there's a minus sign here. So this is orthogonal to this. The inner product is 0, and it says that the expectation value of sigma z is equal to 0. Sigma z in this state, not any state, but in this state, is 0. Let's try sigma x. Let's try sigma x next and see what we get. So we have sigma x here. All right, let's build our sandwich again. We have a minus sign here. And what happens when sigma x equals up, down? It hits up, down. It flips up to down. Sigma x is the flipper. And it flips the first entry here. So it flips the first entry to down and flips this entry to up. We're taking the inner product with this vector over here. So let's see, is there anything in common over here with something in common here? No. So there's no way to get an inner product. Down, up with down, down is 0, et cetera, et cetera. Again, this is 0. So sigma x is equal to 0. Expectation value. Okay, what about sigma y? Let's put sigma y there. Sigma y is also a flip-flop operator. It flips up to down and down to up, but with an I. I don't remember where the I goes. It either goes here, here, something like that. But whatever it does, it flips this up to down, so we get a down, down, and it flips this down to up, so we get an up, up. Again, no inner product, it's 0. So there we are. All 3 components have 0 expectation value. But that's funny, because we proved, well, we didn't prove, but I told you that if I take any state of a single spin, it is never the case that all 3 sigmas have 0 expectation value. What's the lesson? The lesson is that there are states of the composite system that can in no way ever be thought of as separate states for the two subsystems. That's what entanglement is. That's an example of entanglement. Yeah.
So one thing you didn't show here, but maybe it's obvious, is that if you do have a product state, then it will satisfy the same property where one of them will be not
Yes,
zero.
yes. That's correct. That's correct.
Is that straightforward to show?
Well, if you show it for the single spin by itself, then you remember the other index just goes along for the ride. So however you derived it for one spin by itself, you'll do exactly the same derivation except put a sort of spectator index to ride along with it. So yeah, it's obvious that if it's true for one subsystem by itself, that it will be true for the composite. What's not obvious is that it's true for one subsystem. Okay, so yeah, so that's an exercise. That's an exercise to show that all three components of the spin cannot, of the expectation values cannot be zero, and that there's always a direction in which it's maximum.
Question? So how do you put a system in this strange state?
Yeah, it's a very natural state to have. I'll tell you, if you have two spins and the two spins are interacting with each other, they will have a, in particular, if they're little magnetic moments, then they will have an interaction with each other which will prefer to make them anti-align. Now, this is anti-aligned up-down. This is anti-aligned down-up. And in fact, this combination here has the lowest energy. This combination has the lowest energy. It has less energy than up-down plus down-up. So if you bring these two spins together and you wait a while, they'll radiate a photon eventually and come to this state. So it's actually not at all hard to get this kind of state. It's rather easy to get this kind of state. And we'll discuss that when we talk about interactions. But it's a typical situation that this is what would a result if you take two spins, put them together, and let them come to equilibrium by radiating a photon. Yeah.
You said wait a while. How long is a while?
A long time.
What determines the length of?
First of all, how close you bring them together. Second of all, how big the magnetic dipoles of the spin are. And that has to do with the strength of coupling to the electromagnetic field. So, you know, an ordinary laboratory situation. In an atom, the electrons are close enough together that they will radiate a photon in not too long a time to achieve this so-called singlet state. This is called a singlet state, singlet. I'm not going to tell you why right now. There are 4 basis vectors altogether. The reason that this one is called a singlet is because there are 3 others which are the triplet. Okay?
Can you get a feel for why up, down, plus, down, up would have higher energy?
Yeah, well, not at the moment, but eventually. I will tell you the answer, though. If you think of these as little angular momenta, and you put them in up, down, minus, down, up, the total angular momentum is 0. If you put them down, up, plus, down, up, the total angular momentum is 1. And energy is often proportional to angular momentum, so, yeah, we can come to that. Eventually we'll come to that. It's a fair question, but let's not try to answer it right this minute. Yeah.
If you take a general state of 2 systems, like we have, is it possible to change the basis such that one basis creates a subspace of product states, and the other is purely entangled states?
You're asking whether the notion of entanglement is an invariant notion. The answer is yes. The answer is yes. There's a very definite quantity that you can calculate called the entanglement entropy, which measures the strength of entanglement, which is not dependent on any particular basis. Now, I might tell you right now, this state, okay, this state does have a special feature that up, down, plus, down, up wouldn't have. Supposing you took this state, and this is a good homework assignment, up and down individually for both sigma and tau can be rewritten in terms of left and right. For example, up is left plus right, down is left minus right, or whatever it is. The square roots of 2 are there, but you know what I mean. Okay, supposing I write this state, I plug in every place I see down, left minus right, and every place I see up, left plus right. What do I get out of this? The answer is very simple. I get left right minus right left. Supposing I rewrite it in terms of in and out, what do I get? In, out, minus out, in. So the structure that this state has, the nature of it, is actually the same in every basis. In every basis, it looks the same. And that would not be true for up, down, plus down, up. Down, up, and up, down, they would get mixed up with other states. There are 3 other states. This is one. There are 3 others. The 3 others are, well, obviously there are 3 others, and they mix up with each other when you change the basis. But this is not obvious. This is not obvious at all. All right, let's do one last thing. I'm not sure whether it'll be the last thing or not. I think it's probably the last thing for tonight. Let's ask now about one of these observables, which is not an observable that can be identified with either subsystem, but which has somehow got to do with both. Right? And let's look at its expectation value. A very simple example. Let's take the expectation value of the product of sigma z times tau z. We'll do that one. We'll do sigma x times tau x. And maybe we'll do sigma x times tau y, or sigma x. We'll try some examples. Let's take the expectation value of this. Now to do this, we again make a sandwich. And all right, so let's do it. Up, down, whoops, sorry. Now I should put the square root of 2 in. The reason I should put the square root of 2 in now is because I'm not going to get 0. So if I really want to get the numerical number, I want to put that square root of 2 in. And here we have up, down, minus, down, up. Also over square root of 2. So in fact, I can take the square root of 2's and put them all into a factor of 1/2 here. This is the expectation value in the singlet state. Here we take the singlet state, and we take sigma z times tau z. Let's see what we get. All right, first of all, when tau z acts, what does it do? Do you remember? I don't. Oh, yes. Tau z doesn't flip. It just gives you a sign which is plus for this one and minus for this one. So we can remove the tau z just by putting a minus sign here, right? Did I do that right? Let me see, tau z. Tau z acts on down to give minus down. It acts on up to give up. So it has no effect on this term, and it changes the sign of this term. I think I did it right. No? Yeah, okay. Minus. Now, what about sigma z? What does it do? It flips the sign. No, it doesn't flip. It gives plus on this one and minus on this one. So it changes the sign of this one. Okay, now we have to put it together. We have up, down, with a minus sign. It's a -1. We have down, up, with down, up, -1. Cross terms give nothing. Up, down with down, up gives nothing. Down, up with up, down gives nothing. there are two terms, you get a 2 over 2. Minus 2 over 2 equals minus 1. What does it say? This is kind of interesting. The expectation value of sigma x by itself was 0. The expectation value of tau x by itself was 0. The expectation value of sigma x times tau x is minus 1. Let's see if we can see why. Look at the state here. In this component over here, obviously, sorry, this was sigma z we were talking about. Sigma z are opposite in both contributions here. Sigma z times sigma z for this piece is minus 1. Why is that? This one's up, this one's down. If sigma z is plus for this one, sigma z is minus for this one, the product is negative. The product is negative 1 for this one also. In fact, if you think about it, this state is an eigenvector of sigma z times tau z. What's the eigenvalue? Minus 1. So in fact, this state is a state in which if you measured the product sigma z tau z, you would get minus 1 every single time. So the expectation value is minus 1. Nevertheless, the expectation value of the individual sigma z's and tau z's is 0. All right, so this is beginning to get some of the flavor of what an entangled state is. It simply doesn't behave like you might expect two separate systems which are just independent and have always been independent. They behave. Let's try. This is undoubtedly going to get boring now, but let's do it anyway. This is plus minus. We'll go back to the original sandwich, but instead of sigma z, let's do sigma x tau x. All right, so sigma x times tau x, it's easy to figure that out. Tau x flips the second entry, sigma x flips the first entry. All right, so this object here simply flips both entries without changing any signs. It flips no entry at all. What did I say? Yeah. So what does it do? It looks like it interchanges these two, right? Interchanges these two, makes this one minus and this one plus. Now what's the inner product? Up, down with minus up, down, minus 1, down, up, or minus down, up with down, up, minus 1 again, minus 2 over 2 equals minus 1. Same exact thing as and what would you guess about sigma y tau y? Now, there's nothing special about the y-axis, same thing. Also has an expectation value equal to minus 1. So, all right, this, again, is telling you very clearly this can't be a product state. For a product state, the expectation value of a product like this would just be the product of expectation values. And that's not what's going on here. So this is a highly entangled state, about as entangled as you can get.
When we take the product of two observables, so that's two operators essentially. So I don't know how I should think of that physically. Is that one observation followed by another observation?
In this case, remember, no, you don't think of, not in general, no. In general, it's just another operator. If it's Hermitian, it's another observable. It can be measured. But in this case, since all sigmas commute with all taus, you can think about measuring them both simultaneously. All right? And in fact, if you measure them both simultaneously, you will simply discover the obvious fact that they are oppositely oriented. All right, let's do one more. Let's do since I haven't worked it out, and I never worked it out, I'm going to work it out right now. Let's do tau, sigma x times tau z. Let's do sigma x, oops, what did I write here? Sigma x tau x, all right. Let's do sigma x times tau z and see what we get. I don't know the answer, so let's do it. I have a suspicion it's no, I have a suspicion. Okay, we'll find out. What happens when tau z acts on this guy here? Tau z, it just changes the sign, right? Tau z, just, if it's down, you get -1. If it's up, you get +1. Say it again. Oh, I flipped them around. Yes, you're right. Good. Yeah. Okay, so tau z sees the down here and makes it minus down. It sees the up here and leaves it alone. Okay, now what does sigma x do? Sigma x flips the first entry, and so it gives minus down, down, minus, now let's see, it flips minus up, up, right? And we have to take the inner product with this guy over here. Well, nothing over here matches anything over here, so we see that the answer in this case is 0. We see the answer is 0. The expectation value of sigma x times tau z, or any non-equal ones, that's equal to 0. Okay. What does it say? Well, I don't know. The main reason I did it is because I was curious what the answer was. But I also did it just as an illustration of the machinery of calculating an expectation value. But these ones tell you clear things. What they tell you is that in a very definite sense, any given component of sigma and tau, the x component or the y component or the z component, are oppositely oriented. It's obvious here that for the z component, they're oppositely oriented, huh? This is opposite to this. This is opposite to this. So in any of the component state vectors here, they're oppositely oriented. But we also found something else out. We found out that they're oppositely oriented in the x basis or in the y basis. Any one of the bases, if you measure any one of the spins, any component of the upspin, basically it automatically tells you what the other one is. What this is telling you, since it's telling you that the product is always equal to -1, in fact, this is an eigenvector of the product of any of these products, it tells you if you measure any component for one of them, that you will get exactly the opposite if you measure the other one. It's a correlation. It's a correlation, it's a statistical correlation, that if you measure one of the components of spin of sigma, then and also the same component for the other one, they'll be opposite. Because it doesn't tell you much if you measure the x component of this spin and the y component of that spin, that it doesn't tell you much. But it does tell you that if you measure the same component of either of them, they will come out opposite. Yeah.
This is Bell's theorem, you know, the John paper. So it applied, I mean, he's dealing with a system where these two spins are emitted in opposite direction, and it seems like it would be an up-down kind of state. Is that right, or is that
No, the kind of states that Bell dealt with were entangled states, up, down, minus, down, up. It's exactly what he's dealt with. Yeah. Yeah.
Will any interaction lead to a state like this?
This? Yeah, almost any interaction between the spins will lead to a state like that. Yeah, but...
Did you say it's a statistical correlation?
Yes, it's a statistical correlation that, Look, at this, to some extent, it's similar to a trivial observation. You know, the way I like to phrase it is I have a penny and a dime in my pocket. All right? I put my hand in my pocket, I take them out, I don't look at them. Without looking at them, I give one to Alice and one to Bob, and then I tell Alice and Bob to take off and, you know, go to the moon and go to wherever you want to go. Then it's going to be the case that if Alice looks at her coin, she instantly knows what Bob's coin is, right? She sees, if I got a dime, he's got a penny. If I got a penny, he's got a dime. That in itself is not surprising. There's nothing, in the past they were together, some correlation was established. What was the correlation? The correlation was a correlation that if Alice has a dime, then Bob has a penny, and vice versa. No other possibilities were possible. So it was a correlation between Alice's coin and Bob's coin, and it was an anti-correlation. If we called heads and tails plus one and minus one, then if Alice's was plus one, Bob is minus one, but the opposite is also possible. They don't know in advance. And yet, when Alice is far away and when Bob is far away, Alice looks at a coin and she instantly knows what Bob's is. I assure you that does not violate the special theory of relativity. And this kind of correlation is this is called Einstein-Rosen-Podolsky correlation, or entanglement. This is the quantum version of that same nickel and dime story, penny and dime story.
Real nickels and real properties.
Yeah. No, there is certainly a difference. There is certainly a difference, but just the idea that by looking at something at one place, you instantly know something that you didn't know a second ago about the other place, that's just statistical correlation. It's a tremendously common thing in physics. There's nothing special about it. The question is, what is it that's special and different about this entanglement? And that's where John Bell found something interesting. He didn't find non-locality, and we're going to talk next time about what non-locality means in physics and what it was exactly that John Bell found. But I'm going to tell you right now, it was not non-locality. It looks like non-locality, and the reason is because you're trying to apply classical reasoning. What John Bell said is you can't apply classical reasoning to quantum systems. That's what it came down to. Quantum systems are quantum mechanical, and if you try to apply classical reasoning, you're going to find inconsistencies. Okay? I can say it another way. I'll tell you another way. Here's a way to say it. Imagine you had a computer and you try to simulate on that computer the quantum mechanics of a single spin. Now here's the way you would simulate it. You would be able to instruct the computer to orient its apparatus in an arbitrary direction. In other words, you would put in coordinates for a direction. And when you put in the coordinates for the direction, the computer would do some calculation, appeal to a random number generator, and spit out a +1 or a -1. There would be an algorithm that would say that if you do it over again immediately, that you'll spit out the next same number again. And that if you do it again, you'll spit out the same number again. But you might then say, all right, now let me make it more interesting by adding in a mathematical magnetic field which allows the spin to precess. What would you do? You would solve the computer would solve the Schrodinger equation, find out what the state was after a little bit of time, calculate the probabilities for up and down, or whatever you decide to measure, calculate the probabilities, appeal to the random number generator, and spit out a number that was statistically exactly what you should get on the average from quantum mechanics. Somebody who came to this computer and started playing with it and doing these experiments, rotating his apparatus in different directions, turning on magnetic fields in other directions, waiting various amounts of time, and then telling the computer, measure this or that component, would reproduce exactly quantum mechanics, at least to the extent that random number generators are possible. They're not exactly possible, but you can make pretty good random numbers. All right. So that would be a quantum, that wouldn't be a quantum computer. That would be a classical computer simulating quantum behavior, where somebody doing a little experiment on it could be fooled into thinking that it was actually dealing with a single electron inside the computer and doing a quantum experiment. You couldn't tell the difference. Now the question is, could you do the same thing for two spins? In particular, I want to do the same thing for two spins, and I want to do it in such a way that one of the spins, all of its data is located in one computer, and all of the data for the other spin is located in the other computer. Now, I can bring the computers together, have wires connecting them and so forth for a while, do arbitrary things, and then cut the wires and separate them. Can I simulate the quantum mechanics of the two-particle system in such a way that it would appear that one of the computers contained one particle and the other computer contained the other particle? Now remember, this is a classical computer, two classical computers. And the answer is that the only way you could do it would be to have wires connecting the computers at all times. You could not do it unless the computers were capable of interacting directly at a distance. But that does not mean that, that the system is non-local. Non-local means that signals can be propagated from one place to another. What it's telling you is you simply can't simulate quantum mechanics in a local way by a classical computer. The logic of quantum mechanics is different. It simply does not allow itself to be faked by a computer unless that computer is connected over large distances into everything in the world. Quantum mechanics manages to do the same thing without having wires connecting things. However, you could ask the question, does that constitute what physicists call non-locality, or what Einstein would have called non-locality? It does not. It does not constitute in any way the ability to send a message from one place to another. But we're going to come to that. We'll deal with that. No, it is fundamentally the inability to simulate quantum mechanics by classical computers unless the classical computers are hooked up in highly non-local ways.
For more, please visit us at stanford.edu.